Thank you very much for having me. And indeed, I will talk a little bit about the topics of Nexus Linguarum. This is the knowledge representation aspect of today's talk. So first, I will talk a little bit about semantic technologies in two contexts. One is the context of knowledge graphs, and the other is the context of language technology. And then we will look specifically into some background on discourse and discourse relations, and then into their formalization in the form of a knowledge graph, at least the discourse relations themselves. We then go on to connect this knowledge graph of discourse relations with a lexical knowledge graph of discourse markers. So these are the items that tell you which discourse relation applies. And further, connect this with a lexical knowledge graph to induce discourse marker inventories for other languages. Finally, I will briefly sketch some future directions. That is the development of a multilingual corpus of discourse and reference, where we use some of these technologies to create and to pre-process the data that we have. Semantic technologies is a relatively broad and sometimes differently interpreted term. In particular, you have at least two communities in a technical context that use this term quite differently. On the one hand, you have people from the area of knowledge representation, and for them, semantic technologies is basically about the providing and the processing of structured information, particularly in the form of a knowledge graph. So this part of the work is a lot about standards and about interoperability and about processing things on the web. And the interoperability aspect is actually what makes it very interesting for all kinds of applications, also in language technology. The other aspect of semantic technology is semantic technologies is language technologies, in particular in the area of natural language understanding. So where you process natural language input and you want to provide some kind of structured representation according to a specific representation formalisms. Traditionally in NLP, we would look at NLU as a supervised learning problem. And that has been addressed in a long-standing series of shared tasks that continue to this day. And typically each of these shared tasks is designated to specific subproblems such as syntactic parsing, named entity recognition, entity linking, reference, information extraction, semantic role labeling, semantic parsing, and so on. Unfortunately, those two communities don't really communicate to each other too well. So the first aspect is something you would see at a conference like the ISWC or ESWC. The second is something you would see at an ACL or at an EMNLP. But there are connections between those. And this is why already 15 years ago, we began to develop a community that includes people both from the language sciences, from NLP, from applied linguistics, so lexicography, for example, or localization industry, but also from industry actually. And one of the goals here was to bring all of them together and to work towards creating more interoperable representations, to create more synergies out of the different data sets that we have. And this includes the development of the application of knowledge representation standards to solve interoperability problems in NLP. This has been referred to in different ways. One of the terms that we're currently using since 2014, I think, is linguistic data science, which again has a number of different interpretations. But the idea here is to bring people together both from language technology or IT in general, but also from the semantic web parts and from areas of linguistics. Because they don't meet, we try to make them meet. So we have this nice course action. We have a number of W3C community groups where we develop standards for lexical resources, for example, for linguistic annotation. And we have events such as the conference series on language data and so Talking about semantic technologies in our context, it actually encompasses both areas. And this is a fragment of the technology stack that we developed in Frankfurt mostly, but that we continue to develop to this day. So if you want to process data, you often have to solve some basic problems before even getting to this data. And one of the very nice pre-processing tools that we have is conmerge. It takes tabular data, TSV files, and merges them, which is basically a wrapper around MyStiff. But this allows to automatically normalize tokenization differences, for example. So this is a very painful problem when working with different data. And it allows to merge annotations. So if you need to split a token, then you need to do something about the annotations. Automatically. It's actually quite nice. But the part where the knowledge representation part is more relevant is the aspect of RDF conversion and enrichment. So we developed a system that's called Fintan, a flexible integrated transformation and annotation engineering platform. And you will hear more about this towards the end of the talk. One of the applications of Fintan is Conal RDF. And as the name says, it takes tabular data as we commonly use in NLP and creates RDF graphs to do some kind of magic processing there. Okay. In particular, this allows you to link or to integrate information from a knowledge graph, like a lexical resource or an ontology on the one hand, and some corpus data that you have. And knowledge graphs we consider here include the Argoni dictionary graph. This is a collection of some more than 3,000 bilingual dictionaries, and the ontologies of linguistic annotation. This is a collection of ontologies that formalize the semantics of different annotation schemes. And this will be applied here to Discourse. And of course, in addition to that, all of this works on top of W3C standards like URI, HTTP, and RDF. And we also contribute to the development of community standards such as OntoLex, the NLP interchange format, or the Conal RDF data. I guess not everyone is familiar with RDF these days as much as it used to be 15 years ago. So I explained it a little bit. In general, this is just yet another graph formalism. So there's nothing new here from the computational side point of view. It has some special terminology, so we refer to the nodes as RDF resources, and we say this is anything you want to provide information about. And we refer to the edges as RDF properties. Also, we refer to the first element of a statement as a subject, to property as a predicate, and to the thing it points to as an object. This sounds grammatical, it's not. Okay. So far, this is just what any graph language would give you. The difference here is that nodes and edges are unambiguously identified. And they are unambiguously identified not on your local computer or in your local database, they're unambiguously identified on the web. In particular, it is required that every node or edge is identified by a uniform resource identifier. This could be, for example, a URL, as you know from the browser. Okay, so let's create some sample data. This statement here says that the concept BMB 1269 is an instance of the concept linguistic system. And this is what I meant when I said everything needs to be identified by a URI. So we have these namespace prefixes, RDF here, and this is expanded to HTTP and so on until this point. So you can translate RDF type to this URL. You can actually open the browser and see what's defined. And this is true for everything in RDF. Some information that we provide about by means of a literal, so a string statement, is that in English, a label for the concept bump is Bambara. Another label in the language Bambara, which is what this @bm stands for, is Bamanankan. And we can also say that bump is a more specific subtype of glottolog mult 1469. You don't need to know what this is, but I can tell you this is the Monday language family. So we have some data here in two visualizations. On the one hand, you have this more or less intuitive graphical view that should indeed be relatively intuitive. But on the other hand, we also create this representation on top for each individual edge. And these representations are isomorphic in the sense that you can predict this one from there and the other way, maybe except for order. The other format, however, is one of the possible RDF notations that you can actually see on your computer, and it's commonly known as turtle. There are some other representations of RDF data, but this is, I guess, the most readable. RDF is not a standard in isolation, but it's actually part of a broader ecosystem. And another component of that ecosystem is the query language Sparkle. The basic idea of Sparkle is that you write triples, statements, exactly as in the form as you would also do in Turtle, but you change two things. One is you have variables, like language here, and the other thing is that you have operators like select and where, as you know from SQL. So what this query does is basically to match any pattern it finds in the data and to retrieve it as a variable binding, and then to return the language name variable. And it's illustrated here with co-highlighting what it should do in this context. So it returns us the language name label of the language that is more specific than glottolog mult 1469. That is, literally speaking, give me the names of all Monday languages. Now, because this glottolog concept stands for Monday. Sparkle, however, is not just a query language. It's also a language that allows you to manipulate your knowledge graphs. And this is a feature we use quite heavily. The main difference here is that we don't use select in that case, but rather delete and insert, and then write to triples that we want to delete and insert. That's questions about this. It should be simple. RDF is a technical standard, and it's often used in the context of best practices regarding the publication of data on the web. And these are commonly known as linked data. Again, a term that used to be a little bit more popular a few years back, but still relevant. Because we still want to publish data in a way that it can be further processed. The first constraint is that we need to use URIs as names for things. So this actually is also part of the RDF system. In addition to that, you want to provide links about to external URIs, because that would allow you to retrieve information from additional data sets outside your own scope here. So if this kind of data, if these URIs in your data, can be resolved by means of HTTP, so like in your browser, and they provide their information as RDF or by means of Sparkle and so on, and they include those links to other URIs, then we refer to this as linked data. Why should we do that? On the one hand, it creates a little bit of an overhead, but on the other hand, it facilitates information integration. On the one hand, using RDF allows us to establish a level of interoperability in the sense that the same query can run over different data sets. Or in particular, the same query language can be used for different data sets. On the other hand, Sparkle supports a feature that's known as federation. That means your queries are applicable to data that is published on the web. It does not have to be locally hosted by you. So you can actually connect to another Sparkle endpoint somewhere on the other end of the world and include its responses in your own queries. So you can literally query the web. And this then allows us not just to have the same query on different data sets, but actually a single query on different data sets on different corners of the planet. So it's a formalism to build bridges. In particular, it is so because most RDF datasets are not provided as RDF per se, but instead they're just provided as a view on the data. So the native hosting is done differently. You just add an RDF wrapper around it. And it leads to more reusable resources and technologies. And coupled with the dynamics of the open source of data movement, this led to the creation of a relatively large number of datasets interlinked with each other and commonly referred to as linked. The linked open data cloud is a collection of resources that are published under open principles, open licenses, and in accordance with the linked data principles. And about, well, 12 years ago, we decided to develop something similar specifically for linguistic resources. So we began to develop the linguistic linked open cloud diagram, which nowadays is a view or a subset of the linked open data diagram, and provides open resources for linguistic annotation. These are the blue ones, most of them corpora. It provides lexical and conceptual knowledge. So these are knowledge graphs, general purpose knowledge graphs, and dictionaries. And they provide linguistically relevant metadata. This includes bibliographical metadata, this includes metadata about languages, about text sets, and so on. And this collection is still I would say that this technology has a lot of potential when it comes to integration between different heterogeneous distributed data sets, but we also need to be clear about the limitations that it has. So it's not the most user-friendly thing to use. In particular, they're not user-friendly enough for something like a linguist. And most people would not disagree with that. However, most users of this technology would not have to work with it directly. Rather, it's a kind of back-end technology that allows different components to talk to each other. And if it's mediated by software tools, then it's only necessary that the data can be prepared for them or by them. And this is what we want to illustrate here for aspects of the annotation discourse. Okay. Because we now do a little bit of a thematic shift, are there any questions regarding RDF technology? Okay, feel free to ask later. Some theoretical background on discourse. There are some non-trivial aspects of natural language understanding. In general, the semantic analysis of individual sentences is an established field of research, and to some extent, certain aspects are more or less solved. However, there is meaning between the lines or between the sentences. And here's a little bit of an example. So when we have these two sentences, Peter pushed John, he was hurt badly. Who was hurt?
Any of them could, but I guess John was.
Yeah, I think John would probably be the default interpretation. Yeah, so this is the result of Peter pushing him. Probably, because if we add a little bit more context, so he was hurt badly, and so the retaliation felt good for a while, then apparently being hurt badly is not the result of being pushed, but the cause for being pushed. And we can make this, we want to have this kind of information. Luckily, it can be made explicit by means of discourse markers, which are lexical expressions like conjunctions, adverbs mostly, but also prepositional phrases, sometimes phrasal descriptions, and so on. So if we have the sentences, John can't go, Mary can't go either, we can use and to assert that this is additive, kind of continuing. We could use therefore to underline that this is causal. There's some causal relation here. We could use however to indicate that this is contrastive, because maybe one of them was supposed to go and they couldn't, or we could just leave it unmarked, and then each of these interpretations would be possible, depending on context. The meaning of those discourse markers is normally described in terms of discourse relations, which are semantic, pragmatic, or conversational relations that fall between an utterance and its discourse context, broadly speaking. You will see a number of varying definitions here, because there are a number of diverging theories behind that, and they diverge a lot. And it's not just theories, it's also data. So if data is created in accordance with one of these theories, say RST, then it's not guaranteed that they can use any of that for training, for developing tools for the PDTB, and vice versa. And this is a problem because the creation of this kind of data is extremely costly, simply because it involves a lot of effort to create. So discourse parsing now involves the question how to identify the relations in order to assess how the utterances are connected with each other. And from a technical perspective, you could use it for information extraction, text summarization, machine translation, and so on. As we go through all those complicated things here, maybe one or the other might not be convinced that this is actually necessary, and in particular in the area of LLMs. However, LLMs are still relatively poor at processing the discourse aspects of natural language. Maybe that will change, but if it's supposed to be changed, then we need some training. The main frameworks in this context here are the rhetorical structure theory, RST, and the Penn discourse tree bank. And we have a lot of multilingual data for them, or some, but unfortunately they're relatively incompatible. So they agree that there are discourse relations, and these discourse relations are associated with certain markers. But in RST, it's assumed that discourse relations constitute a tree structure, and that all utterances in the text, in the discourse, must be connected to this tree structure. And sometimes this is referred to as deep discourse parsing. In the Penn discourse tree bank, people figured that it was too hard to annotate trees, or at least to annotate trees in a way that people actually agree upon them. So they made the decision to forget about the tree and just to annotate relations wherever they saw them, or wherever they thought they could infer a connector or insert a connector. And this is referred to as shallow discourse parsing. However, there are some pieces of data that are actually annotated for both theories. And even in the areas where they don't contradict each other, so you could say that every RST tree could be represented to a PDTB representation, they often do. Unfortunately, that's not very readable, but I have this visualization to indicate what is one of the differences here. So in the RST discourse tree bank, it basically treats these two utterances together and then says this is the argument of the last thing, then compasses all three of them. And in PDTB, it does it the other way around. It says these two belong together and this. So what to do with it? And it's not the only problem, because they also disagree on the kind of relationships. So the goal here is to consolidate and to integrate existing data sources across languages, in particular to support the processing of multilingual discourse markers across frameworks, at least RST and PDTB, across formats, because they come in very different shapes, and to provide machine-readable semantics. That is, to connect them with knowledge graph, because the knowledge graph would exactly help us with the cross-framework approach or problem. And this is the next aspect. And as you see from the date of the associated publication, This has been done 10 years ago, so it is like aged wine, but still relevant, I would say. An ontology can also mean different things in different contexts. In this context, it means a formalization of concepts and their relations for a particular domain, like an area of terminology, for example. Formalized in terms of the web ontology language, which is one of the W3C standards for vocabularies for objects. So it's a vocabulary for classes, concepts, properties, relations, and axioms that hold them together. Selected properties here include RDF type that is used to assign a class or a type to an object, RDFS subclass of that basically is a subclass of relation between two classes, but to some extent it corresponds to the logical inference. Intersection of, which roughly corresponds to the logical and, a union of, which corresponds to the logical or, and complement of, which corresponds to the negation. And as you might see just from these terms, this is a fragment of predicate logic. So this is the kind of semantics that we want to provide. The ontologies of linguistic annotation have been developed to provide this kind of information for annotation schemes. So you basically take the documentation of your annotation scheme and you create an ontology out of that. That follows the documentation. So you create concepts, instances, and relations between them as they are documented in this. For a particular text set, we then have one annotation model, which is a separate ontology. And in addition to that, we have an overarching ontology that provides reference types that are used in different corpora. And that provides common terminology. Separately from both of these ontologies, there's another RDF file, so an ontology that imports both reference model and annotation model that contains the linking between both of them. And the linking is implemented by subclass of relationships. We have such schemas for more than 100 languages, mostly for morphosyntax, inflectional features, and syntax. But, as we'll see in a moment, also for Discourse. Let's take a look how this works. So STTS is the default text set for German, and we have a tag which is PDAT. This tag is a string value PDAT, and it's defined in the annotation model as an instance of attributive demonstrative pronoun, which is where this A, D, and P come from. Which then is a subclass of demonstrative pronoun, which then is a subclass of pronoun. It's exactly what's important in the order of characters. However, here it's represented in an ontology. We have the reference model that doesn't use the term attributive pronoun, but it uses the term demonstrative determinant. So the determinant in this context corresponds or includes attributive pronouns. So the linking model says that the attributive demonstrative pronoun is a subclass of demonstrative determinant. Yeah? And within the reference model, we then figure out that this is a subclass of determinant, pronoun, and determinants. And we have that for a number of different annotation schemas like STS for German, universal dependencies, you name it. Also, the same mechanism is used to link the reference model with other existing vocabularies, like, for example, the Clarion concept registry, or the old ontologies from. The adaptation of that to Discourse basically means that we create annotation models for RST, PDTB, and the respective corpora. But also we need to extend the reference model. And this has been done 10 years ago, as I said. Basically, the ontology is encoded as a taxonomy that reflects the internal structure of the text set. If you know about PDTB, you will recognize those nodes: temporal, expansion, contingency, and comparison. And they have various subtypes which are just reflected in this hierarchy. The reference model is, for this case, actually based on the PDTB, but it has been extended to cover RST and the other corpora. So normally we did not merge things unless we were very clear about the definition, but we sometimes inserted nodes that were specifically defined for a particular theory. So for example, here is restatement, and we said that the definition of elaboration generic specific in RST would be a subclass of restatement. You might disagree on that, but that was the way that we did it. Also, it was linked with meta vocabularies like the CCR and the ISO semantic annotation framework part for discourse relations. The linking between them basically involves a single triple stating that one element from here is a subclass of one element from here. And we can apply that now to the example that we had. And in order to do that, we need to figure out what to do about the different segmentation issues. And for the sake of presentation, we just say we focus on the discourse relation that is the minimal span connecting argument 4 or utterance 4 and 5. And then we see that the relations actually match quite well. The RST side, we have condition. On the PDTB side, we have contingency, condition, general. If we then look into what the ontology tells us, then we can infer all these superclasses that we had in the tree. So from the PDTB side, for example, we would infer that it's a general condition in the sense of PDTB in the reference model. So this is here. So this is the annotation model. This is the linking. This is the reference model. But the concept was marked for coming from PDTB because it was specifically created for the purpose, because it doesn't ensure that the definitions were actually identical. Within the reference model, we then say that this is a subclass of semantic condition, contingency, and so on. If you're coming from the RST side, we have the RST condition, which is a subclass of Molière semantic condition, and you see this is the same triple as here. So far, this agrees, but there's some information that's specific to RST, and this has to do with the internal tree structure. So we don't get this part from PDTB, but only from RST. So even though these annotations are not quite alike, they agree on a number of statements, which are exactly those highlighted here in the bold case. And we can use those correspondences in order to compare across frameworks, as we did for the example. But also, we can actually use them to derive a mapping from RST to PDTB, or vice versa, or into any other thing that has been. Maybe the mapping is not precise. We can even measure how precise it is, but we can just develop our own heuristics as part of the search process. And this search process involves to find the shortest path of an element from this vocabulary to an element of this vocabulary. Yeah? And by using Sparkle to basically iterate over the path, we can also track the length of the path. Okay, and this brings us to the linking of discourse mark inventories. So what we get from here, the component we will continue to use, is the translation between PDTB and RST, or any other annotation you want to test. This translation can be done on the fly, without losing any. The most elementary step in doing discourse annotation is to identify discourse markers and their respective relations. At least that's the point you commonly start with. And then to think about implicit. And for a considerable number of languages, discourse marker inventories have been developed. to facilitate the parsing and other downstream processes. In particular, they include not just listing the markers and their grammatical conditions, but also the possible discourse relations they can be associated with. But typically, these discourse relations are defined in accordance with one particular theory. And that means we have different formats, we have different frameworks, and the contribution here is to consolidate and integrate this a little bit. Indeed, this has been done before, and I know that you've been involved in TextLink as well. It was another cost action a few years ago, and one of the results was to provide those multilingual discourse marker inventories. Most of them provide the senses in terms of PDTB, not 100% systematic, but almost. Most of them provide it in accordance with a consistent XML format. Not all of them, but most. And you can actually use that data or browse that data into OntoLex.info. However, this website and the data itself at the moment is available and usable only for human consumption. So if you want to know something about the discourse marker, you can look at that. But you want to have it more processable. So we aim to improve the coverage in the sense that we want to add languages not addressed by TextLink and language resources not addressed by TextLink. We want to provide machine-readable semantics because this is what the XML format doesn't do. It provides labels. Some of them are well-defined, but sometimes you just have a typo. Things don't work anymore. But at the same time, we also want to preserve anything we get from the original. So we don't want to normalize against yet another standard inventory and thereby losing information that they had in the original data. And we want to have it usable in the sense that we want to enable cross-framework comparison and search. And of course, linking and querying across languages. So what we did was to create an RDF edition of TextLink and other discourse marker inventories using yet another RDF vocabulary, OntoLex, which is normally used for providing machine-readable dictionaries. We maintained the original sense definitions, discourse relations, and then we linked them with the OLIA annotation models that we had from the last. And this then allows us to flexibly map between different frameworks by just traversing the ontologies by means of Spark. So we get from PDTB to the reference model to RST, or to ISO, or to CCR, or whatever. Let's look at an example. So this is a DimLex XML format for German, and I think it's a kind of prototype for most of the other discourse marker inventories. And if you look into OntoLex, then this defines core data structures you would expect in a dictionary. This includes the lexical entry. And the lexical entry is defined as something that comprises a number of forms on the one hand and a number of senses on the other hand. So these are the forms, these are the senses, and there are some relations between. And this is all the structures that we find in the XML format on the other dictionary format. So here we have an entry element that clearly corresponds to this lexical entry. It gives us the form, aber, but. Here we have an ORT element that corresponds to the form, which again gives us the form for the canonical representation and also for other representations if they exist. And we have a SEM element, which provides us with a value for a sense. In this case, concession arc2 as denier. In addition to that, we have a lot of information that we cannot map. And this includes the non-con reading, different examples, syntactic information. But the nice thing about RDF is that we don't need to normalize anything into a fixed tabular data structure. But instead, we can just create our own properties whenever we need them. So we just create one property for every XML element that's not covered by the default mapping. And this is what we did. So we have a DimLex namespace that basically corresponds one-to-one to the structure that we have in XML file. And for the interpretable elements like entry and form, we have the standard OntoLex terminology. And we applied this to all the TextLink inventories and to some additional inventories. It's a little bit more than just a conversion because we can now do novel things, like, for example, processing this graph or visualizing this. So this is the same information as you have here in the XML. The linking between those kinds of mini graphs to OLIA can be done in a very simple way. And you might maybe not agree on this being a very trivial Sparkle update, but in the end, it just means the following. If we have a DimLex relation that has a sense label, and this sense label matches the label we find for a PDTB sense, then create a link, an OntoLex reference link between the DimLex relation and the PDTB sense. It's a little bit more complicated because we do lowercasing here and things. But in general, it's really just a lookup. Find the same string in two knowledge graphs and create a link. The advantage now is that this link can be used for traversing in search. So we don't need to map it every time. And that's the result here. We have a number of inventories for, so 19 inventories for 16 languages. In TextLink, these were mapped to the PDTB ontology, and we found this also to be applicable for disk mark inventories, for example, which are not part of PDTB. I think one of the others is also not part. In addition to that, we're not just linked with PDTB, but via the OLIA discourse model, we're also linked with RST and other models. And we're also linked with the meta frameworks like the CCR or the ISO definitions. So we can use path traversal in this knowledge graph to give us ISO, CCR, whatever definitions for any discourse marker from any of those schemas. The main difference in comparison to TextLink is not that the data is of superior quality, not at all. The main difference is that we now provide cross-lingual and cross-framework integration, and we can actually use it for search. And once you have such a query running, you just need to adopt it. So we don't need to develop it every time from scratch. So this is one of those queries, not exactly trivial, but not very hard to modify. And I'm explaining briefly the structure. In the first part, these from statements, we provide the addresses under which we find the different knowledge graphs. This is the PDTB dataset, and this is the OLIA dataset and the RST dataset. Then we look for the label because in OntoLex, and we go there to the lexical entry, or to the lexical sense to be precise, which is this PDTB element. This PDTB element from the discourse marker inventory is then used to retrieve subclasses that might be associated with it. In particular, these RST subclasses are all a little bit more fine. And then we follow that and return the RST subclasses, so they need to match that pattern discourse.rst. So in the end, this gives us a list of possible RST interpretations of because, as because is represented in PDTB2. And this is the list. So for the PDTB variable, it says it's cause or condition. In OLIA, this corresponds to cause or condition. And in RST, this corresponds to a large list of relations. Maybe some of them are more specific, but you have some default semantics involved here. So most of them because should be a possibility. Okay, now we connect this kind of information with a lexical knowledge. This lexical knowledge graph is the Arcoli dictionary graph. It covers 430 languages and 3,000 bilingual dictionaries. You have here this plus because we only count datasets for which we have 10,000 translation pairs. Because some of the datasets are multilingual, but then you only have very few items per language. This is basically an RDF layer defined over existing dictionaries like Panlex, Apertium, Fredict, Muse, and so on. It uses the OntoLex vocabulary that was mentioned for the discourse marker inventories. So the native format is RDF, but we generate a TSV, tabular representation out of that by means of Sparkle. In order to keep things manageable for this little experiment we did, we focused on 3 subsets. One was a Persian, which is 53 dictionaries developed for machine translation, mostly, but not exclusively, Romance languages. FreeDict, which consists of 145 dictionaries, partially crowdsourced, partially converted, very heterogeneous. And Muse, which consists of 108 dictionaries, all of which were machine generated, basically extracted from translation tables. Okay. Over this lexical graph that is constituted by the individual dictionaries, we then performed a constrained induction. This is illustrated here for 4 languages. We have Catalan, we have Esperanto, we have Spanish, and we want to predict the English. So let's assume we know that Catalan C is temporal. We give the score 1.0, and we see it's translated to Sino in Esperanto, for example. But Sino does not just correspond to C, but also to Sina and Interior. So we just estimate the score here by dividing that by the number of incoming edges. And we continue that to the next layer. But here we also take other incoming elements into account. So we generate an aggregate score for every kind of discursivation we want to induce out there. Unfortunately, this generates a lot of noise, and it also generates a lot of potential assignments with very low scores. So it makes sense to filter that, for example, by requiring that we need a minimal score, that we need a minimal number of translations between a translation pair, that we need a minimum number of languages for doing this kind of induction, and also that we need to do some kind of pruning, so we only consider the top K conditions in the end. This procedure, with all these variations, was applied to this graph of dictionaries. Actually, the graph is not a graph of dictionaries, but a graph of languages. Every bubble represents a language, and every edge represents the existence of at least one dictionary in between. The bubbles with 2 circles around them are those with discourse marker inventories. So we have 11 inventories, 9 languages. We use them in the form as they're mapped to PDTB into CCR, and then we evaluate it for precision recall and F-measure against the target inventories that we already had. Along the way, just indirectly by going over these, we also induced a number of additional inventories for other languages, and we published 10 of them for Bulgarian, Greek, Esperanto, Finnish, Japanese, Norwegian, Polish, Russian, Swedish, and Turkish. However, these are not post-processed, but just published. And they need to be post-processed, because if you look at the scores, then you see that sometimes we get really high recall, like here, more than 80%, but usually it's a lot lower. But even worse is the precision. However, that doesn't matter so much, because these discourse marker inventories are tiny, and we can return the result ranked by the respective scores and ask a native speaker to tell, is this a discourse marker? And if so, is this assessment right? And you only need to do that for maybe 1,000, 2,000 words, so it can be done in half a day. We tested different constellations. Direct induction over aggregated dictionaries can give us up to 80% recall when you optimize for F. But the average score is a little bit lower, so this is around 68% recall. The difference between those levels here is that the PDTB hierarchy has a top layer, a middle layer, and a bottom layer. And if you just want to predict the top layer, then this would be level 1. The second layer, level 2, the third layer, level 3. And we projected them independently, and we elevated them independently. If we do that over all the languages, so not direct induction, but indirect induction, we actually see that it's not much worse than the average performance for direct induction. So it seems to be a viable fallback solution. However, in any case, that requires manual pruning. But again, this is not a problem because Discourse marker inventories are not that large. Well, as we're getting more so, this is the top level of the Polish inventory. And it pretty clearly says that dlatego is contingency, and in particular, result, whereas everything else has so minimal scores that you can basically forget about it. So I'm not sure whether this is true, but this is the statement it's most confident. For Zatem, apologies for my pronunciation. It also predicts contingency at relatively high scores, and also says it might be a result, but it also gives a relatively high score to temporal. Not sure whether this makes sense, but a native speaker should be able to verify. And if you go further down the list, you find a lot of noise, a lot of things that are not a dictionary, discourse marker at all. So then you basically just stop and say, as of this point, I haven't seen discourse marker since half an hour. That's enough. There are some limitations. This approach will only work if the discourse marker is actually in a dictionary. And for a lot of phrasal expressions, they won't be in a dictionary in the first place. So you need to do something about this. Other possibilities, like doing this by corpora, or like doing paraphrasing tests, or like using that to suggest you some paraphrases. But at least this gives you a kind of seed for discourse marker inventory. Okay, and basically these were the core components of what I wanted to present. Now is a little bit of an outlook, because we will use parts of that in the creation of a corpus with annotations for discourse and reference. At the moment, so far, we have a number of multilingual discourse marker inventories, as known as graph. We have a technology to induce discourse marker inventories for actually hundreds of languages. And you can flexibly switch for any of them from one theory to the other. And this can be used, for example, to create free annotations for discourse annotations in a new language. This technology can also be used to convert one corpus from one framework to another framework in order to increase the amount of training data, for example. But one thing we did not address so far were actually these structural differences that we saw in the diagram. We only addressed the relations. And for this specific case, RST and PTTV, this has not been done, but we have the right technology in place. So take a corpus, transform it into an RDF graph, apply Sparkle updates for enrichment and transformation, and serialize that into a target format. Has anyone any real experience with RDF? It can be a negative. Very small? Okay.
Several years ago, yes, and with Protege and ontologies.
Very nice. Then you might know that the last three statements here, this is actually scary. This is super scary because, well, that's a performance nightmare. You have these huge graphs, and you want to connect all of them and do some induction over thousands of languages, if possible. That won't work, not at all. And this is why, by the right tooling, I don't mean off-the-shelf RDF technology. What I mean is the flexible, integrated transformation and annotation engineering platform. At its core, it provides a conversion between NLP formats and RDF graphs, but it does so one sentence at a time. Plus, you can define that, the context before and after, as measured in a number of sentences. And this is important because this guarantees that it fits memory. So you can play around with these parameters. You don't need to put everything into a single database. Also, it allows us to perform stream processing. So you can already pipe your corpus through and not wait until everything has been applied to the entire dataset, but you see your results basically immediately. And it can be parallelized because you process each sentence plus context independently. You can run it in different threads. And we can at least outperform generally. physically, relatively easily on the call. Fintan was developed in the project Pratalot. And the goal was to transform heterogeneous data, in particular language technology data, in a unified way. So we can convert any kind of language resource to RDF graphs, not just corpora, but also dictionaries. We can manipulate it, link it, transform it by means of Sparkle. And here I mean Sparkle update. So you can insert and delete things. We actually extended Sparkle in a way in that we introduced loops. So you can do the same replacement one after another. And this means that this is NP complete. So you can literally program anything with Sparkle if you want. You shouldn't, but you can. And then you serialize that back either as RDF or in the conventional format. The nice thing here is that it's modular in a sense that the transformation pipelines are composed of small reusable pieces. So this is the components to read and write this data, but also to transform it. But these components to transform it are just individual Sparkle updates. Using Sparkle also means that it's reusable. If different data sets use the same RDF vocabulary, you can apply the same Sparkle. It's extensible, so you can write your own Sparkle transformations, but also you can include Docker components or native Java components. So this is written in Java. In particular, those Docker and Java components are important if you want to add a new format. And it's scalable, so it supports stream processing and parallelization. We have a default repo that contains everything, if you will. This is in the Pratalot GitHub. But also we have a special customization for common data. So this supports some of the data structures that have been invented to make things representable in a table that should not be represented in a table, like semantic role information, for example. Okay, and this is how it looks like. So you convert or load some data from different formats. Then you have a definition of a workflow, which basically means identifying this input component and this output component, and then define what kind of transformations to apply. These transformations can actually exceed beyond the data they read from the input, but they can also consult other knowledge graphs along the way, like, for example, Wikipedia or the ontologies of linguistic annotation, and so on. And then we spell everything out and return audio formats, conventional formats, whatsoever. Fintan has been used for different conversion and enrichment or linking tasks. One area where I see a lot of potential is the rule-based post-processing of automated annotation. So if your parser produces something that you don't really want, or you want to extract something from this, you could use Sparkle. This can also be used, and we have done it, for querying over heterogeneously annotated corpora. So we set up an environment in which we could query across all corpora of syntactically annotated historical German, going back for 1,000 years. Even though they were vastly different, we could use the same Sparkle queries to run over them and to answer some questions about historical syntax. We also created a semantically annotated tree bank in accordance with role and reference grammar. You might not necessarily know about this, but it's a bit special in a sense that the clausal structure is defined by semantics, mostly. So if you have two clauses that overlap in one semantic argument, you must use a different kind of coordination. So what we did here was to use QD parsers and prop bank annotations that we had for the same piece of data. We decomposed it and we recomposed it in accordance with role reference group. And that was quite a task. So we needed, I think, 250 Sparkle update statements in between. That's also not very, very fast. But I don't think it would even have been possible with any other technology. And the last thing, and this is what I wanted to conclude with, is the pre-annotation of the Augsburg corpus for reference information. There we did the automatic pre-annotations for discourse markers and for the language-specific classification of referring expressions. This language-specific classifications involves, for example, to tell whether something is a possessive noun phrase. So this is not anything you can immediately read off from UD annotations, because UD annotations are different. Some say n mod pos. Sometimes the annotation of a possessive pronoun is just missing. So I think for Portuguese, so you need to know the specific lemmata of the pronoun that is used there in order to tell that this is a possessive construction. But it's fairly easy to do that in Spark convention. And also we converted existing annotations from other corpora over the same texts that we use. So Discourse is an annotation of the parts of the TED Talks and use. And TED-MDB is one of the schemas that were mentioned in the slides at least. And we converted that to the schema of OntoLex. In general, the situation for the study of these areas, reference, information structure, discourse structure, is that we don't have as much data as we would like to have. So we need to think about how to create more. And since I've been in Augsburg, I started to begin to develop such resources as part of a general courses. So with students from the phonologies, mostly in seminars with students from German linguistics, English linguistics, Romance studies, and translation science. So this poses a number of specific challenges, including we must be sure to use a very minimal technical entry barrier. It must be something that everyone can be using, regardless of their tools. It must be something that supports both online editing, because some people just don't have adequate equipment, like only a tablet. And it must support offline editing, because a lot of people commute. It's nice to do those things on the train, but we live in a mountainous region. There are a lot of tunnels and Wi-Fi breaks down. It must be multilingual. So students must be able to do the same task as other students over the same text. That is, everything in our corpus needs to be translated in at least a dozen languages. And of course, we need to do some kind of evaluation. We don't have a great pool of annotators, and this is why we resorted to convert annotations and then use that as a baseline for comparison. So the minimal technical entry barrier, we thought a lot about that. And maybe that's not the most popular decision to take, but we thought generating spreadsheets is not the worst thing to do if you constrain the possibilities in a sufficient way. And if you help the annotators with visualization and some pre-annotation. It also accommodates this offline and online editing requirement. We have multilingual data in 400 to 750 languages, from literature, Bible, but also regular literature, from news texts and from TED Talks. And we created some existing annotations to evaluate students by bootstrapping the annotations from the TED-MDB and from Discourse. This has been done already. And OntoNotes and FrameNet, implicit semantic role labeling, has not been done yet. And this is how it looks like. Preprocessing is done by a parser according to UD, in order to be applicable to do this for any language we need, and by Fintime. And Fintime reads in lexical lists like this list of discourse markers, for example. And then we generate a spreadsheet, including the layout and including the formula that calculate or that predict the values for respective columns. We also we also generate the locking mechanism, so you cannot edit here. The text stays intact. On the discourse level sheet, you see basically one sentence at a line. This column says text. We give every sentence an ID. This is important because we cannot annotate relations. We'll need to refer to those IDs. And we use UD to spot the main predicate. This is the syntactic root, unless it's an attribution, and then we go into the statement and try to find the syntactic. The marker column is automatically pre-annotated by using a discourse marker inventory. And if we don't have one, it just has 3 exclamation marks. The target needs to be manually inserted here, so it should be one of those IDs. And the relation label also needs to be manually inserted, but we could think about predicting it from the most frequent relation per Discourse. This kind of annotation also accounts for annotating implicit markups. So we can ask annotators to say, what would you insert here? And whatever they would want to insert, they can just type in here. And for word level, so this is mostly reference annotation in this column. We use UD and Fintan to identify the grammatical role and the depth of syntactic embedding of different referring expressions. We have an elaborate taxonomy of inventories, where we have relatively complex patterns that we could easily implement with Sparkle. And we have a prediction as to whether something might be anaphoric or not. The task for annotators is to annotate everything that has been suggested as being anaphoric, and then they see those exclamation marks. The other columns here are pre-populated by means of Excel formula. So for example, if you have a reoccurring element, then it will give you another value for referentiality, like this has been previously mentioned. Okay, basically, I think that was it. I presented a number of technologies and resources designed to support aspects of discourse processing and discourse annotation, in particular RDF technologies and big data, and their application to establish some level of interoperability between theory-specific inventories of discourse markers. Also, to access those discourse marker inventories as a knowledge graph, to link them with inventories and to map their respective meaning and to other theoretical frameworks, and to link them with a lexical knowledge graph in order to do lexical induction of discourse marker inventories for other languages. And then some remarks, I wouldn't say I showed it, but I just claimed it, that we could use the similar kind of technology also to convert or to pre-annotate annotations for discourse and for reference. I would say that RDF technology in general has a lot of downsides. So it's bulky, it's not very readable, it has a high entry barrier. People are just not being taught that at universities. So you need some kind of special education. However, it can be used for a lot of different scenarios in which you need to integrate different kinds of information. And I think in discourse studies, you really do. For example, to provide training data that comes from one framework, but you need another form. And I think there's a lot of potential here. But it has some learning curve, and this is why we, and as one of the very last things in Nexus, we set up a massive online course on linguistic linked data. And if you're interested in learning more about this, then we have these nice QR codes here. So this is the basics, 15 hours, and this is advanced. But you can skip any topic you don't need or that you are already. Okay, so thank you very much. I looked up what thank you in Polish is, but I didn't dare to pronounce it.